Okay, in this video clip, I'm going to finish the first chapter and we're going to talk about the reasons why we need um, dynamic simulation models to address spatial phenomena. Okay, and firstly, we need to know that there is always trade-off in modeling among generality, realism, and precision. Okay, when we are trying to create models, we we can achieve two of the three, but not all three of them. So it means that in order to pursue two of them, you have to sacrifice the rest one. Okay, and analytical models, they are usually pursuing generality, which means analytical models, when they are established, they should be able to uh, be applied to different scenarios, can be widely used. Empirical models, they are pursuing precision. They're trying to predict things, but not necessarily accurate. But you should know that empirical models, they only care about the statistical relationship between or among variables. And simulation models is somewhere between analytical models and empirical models. They are trying to be uh, closer to the reality. Okay, and some examples here. The first example is called Van Thonen model of land use around a market center. Here we have a very general model. Because it is pursuing generality, this model can be applied to any market center. So here we don't have the shape of the market here, or the farms or the ranches or the forests surrounding this market. We only have concentric circles, each one representing a specific land cover type or land use, right? So this is a general model, can be applied anywhere with a market center. Okay, usually the surrounding land cover land use types have been decided or not have been decided. They will generally follow this model. Another model here, analytical model here, is called central place theory of the location and size of cities as market centers. So in this model, we can say it's still very general. There is no specific shape for city, for town, or for market town. Each specific geographic entity here is addressed by a hexagon, right? And this model, again, it can be applied to any location around the world with cities, towns, and market town. This model is telling you that this is the general distribution or the spatial relationship among these four types of land use. But what's the scenario? What's the specific situation, specific spatial distribution of these entities in your area? I'm not sure, but I gave you this very general model to address a widely used a scenario that can be widely applied to different locations. Okay, so generality here is the main character. Okay, analytical models, usually they should be able to get applied to any locations. Empirical models, statistical models, a very typical example should be GWR, geographically weighted regression model. For example, here is a figure from a research applying geographically weighted regression for house prices in Michigan. And what is a GWR? A GWR regression means that the locations of independent variables affect the dependent variable. For example, here, house. Obviously, house price is severely affected by its location, by the location of a house and its surrounding environment. Okay, GWR is trying to address the importance of location in spatial regression. Okay, if there is no spatial context, a regression is a regression. But since we're talking about geography, location matters, and the location should be addressed in your regression, especially for a research subject such as house price. Right, it should be dramatically affected by its location. So GWR, it is trying to pursue precision or a prediction, and you should know that these empirical models, they are established based on some data sets, because it's statistical relationship, and due to this reason, these models, they should only be used locally. For example, in this research, the GWR model is established on the datasets from this specific area in US. Then this model should be only applied within this area. And if you use the same model for other areas, you will probably get incorrect or inaccurate results. So that's the disadvantage of empirical models. They are local. They are established local. They should be used locally. Okay, there is no generality in empirical models. So simulation models, it is pursuing. They are pursuing realism. Okay, here we can say it's a research about the prediction of land cover change in the next 100, not next, from 2000 to from year 2000 to year 2100. So obviously it's trying to predict, but we should say that this model is somewhere between empirical model and analytical model, because the trend, you can compare these two figures. The trend of land cover change here is not exclusive to this area, because you can say that on the left side, in the central part of this area, this dark yellow area is agriculture in 2000. And according to this model, in the next 100 years, a dramatic part of this area will be changed to what? To developed. This is a trend that is happening everywhere around the world, urbanization. So you can tell that this simulation model has some generality in it. And what about the empirical part of this model? This model is based on a specific area, right? For this specific study area. This model is based on the data of this area to do the prediction. So there is some precision in it. You cannot say that this model can be used anywhere around the world. It's still local, but not that local. So you can say realism, simulation models, they are somewhere between generality and precision, or empirical models. Analytical models and empirical models, they are two extremes. Realism is somewhere between them. Simulation models, they are somewhere between them. And some examples here using models to address patterns. Two simple but common ways to model observed data. The first one is called additive processes. We usually use normal distribution to address that pattern or those processes, additive processes. And we use another distribution is called log normal distribution to address multiplicative processes. Okay, and this model here we can use to address these two distributions is called Galton board. It's a physical model of normal and log normal distributions. Here we have two Galton boards. The left one is used to address normal distribution. The right one is used to address log normal distribution. So let's check the left one first. We have this Galton board made by a lot of small triangles, and we have a funnel here above this board, right, with a lot of steel balls, and each ball will just drop from the center of this board, right? This is the central line of this board, and each steel ball will drop here, encounter the first triangle. It could go left or right. The probability is 50-50. And then encounter the next triangle, left or right, 50-50, and repeat this process until that ball reaches the end of this board and drop into one of these small boxes below this board, below the Galton board. So most balls, we know that they will drop in the center, in the central box, because it's most likely that a ball will go left, then right, then left, then right, because it's 50-50. It's not very likely that a steel ball will go left, 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 straight left to the extreme left or extreme right. So that's the reason eventually we have this normal distribution, right? For most steel balls, they are in the center of this distribution, which means that if a ball is dropped right here, it's most likely that it will drop into the central box here. That's normal distribution. And this is a process called additive process, because for each triangle, the probability is 50-50. And no matter a ball goes left or goes right, the distance it will travel from the central line stays the same, because all triangles here, they have the same size. But on the right side, it's different. This is a Galton board for log normal distribution. So the first difference is that these triangles, they do not have the same size. The triangles on the right, they are larger than the triangles on the left, which means that these triangles, they're trying to make a process called multiplicative process. It means that the movement of a, or you can say the encounter of a ball and a triangle is affected by the encounter before. For example, if a ball drops on this triangle, it could go left or could go right. But if it goes to the left, it will encounter a smaller triangle, which means that this encounter, no matter it goes to the left or to the right, it will travel a less distance to the left or to the right compared to the first encounter. And if this ball goes to left again, there will be an even smaller triangle. And no matter it goes left or goes right, the travel distance will be shorter than the last one, because the triangle becomes smaller and smaller. So you can say each encounter, when we're talking about the travel distance from the central line, each encounter's travel distance is affected by the last triangle, by the last encounter. So this is a multiplicative process, which means that each step is affected by the last step. Okay, another difference is that these steel balls, they are not dropped from the center of this board. They are dropped on the left, from the left side of the board. So eventually we have this normal distribution, like distribution, but not normal, with a long tail on the right side, on the right side. So this is called log normal distribution, because if you calculate the logarithm of the normal distribution, you will have the log normal distribution. That's the reason why it's called the log normal distribution, and it is used to address a multiplicative process instead of an additive process. Okay, so this is a physical model to address pattern. What pattern? Normal distribution, log normal distribution. And from abstract to realistic models, they are models pursuing realism, or in other words, they are what? Simulation models. So general models, they are based on general processes. For example, normal and log normal distributions. Model simply says the unobserved process is independent or dependent. And these models, they can be applied anywhere. Normal distribution, log normal distribution, they're everywhere in our daily life, in our society. So these models, they are not for specific phenomenon or for realism. They can be widely used anywhere. Specific models are based on specific process. This is what? This is for simulation models. For example, how does the independent or multiplicative process occur? So there is this conflict between being specific and being very general. So must we lose generality with a highly specific simulation model? The answer is not necessarily. If we know, we are alert to the similarities between patterns across diverse domains. For example, segregation and aggregation in a city and a forest. Once we establish a model to address segregation and aggregation of different groups in a city, we can use it to simulate a forest, because a city and a forest, they share similar features. Segregation and aggregation in a city is relatively easy to explain, right? People, although we don't want to see that, but the fact is that different ethnic groups, different people with different income levels, they are segregated from each other in a city. There are expensive communities, less expensive communities, or communities with very cheap houses. It's a fact. It's a fact. So since there are segregation simultaneously, similar people, they are living together, they stay together, that's aggregation, right? That's for a city. If you have a model for a city to address aggregation and segregation, you can use it for a forest, because in a forest, it's the same. It's not the same, it's similar, right? Similar species, they tend to get together, to live together for their survival. So this is aggregation. Since there is aggregation simultaneously, different species, they are separated from each other. So here we have a specific simulation model for city, but this model has generality. We did not lose generality by creating a specific simulation model for city, because as long as the pattern behind this model can be shared by another entity, by another phenomenon, for example, a forest, it can be used in other scenarios. Okay, so generality and being specific, there is conflict between them, but it doesn't mean that they cannot coexist. Right here is an example. Segregation and aggregation model for a city can also be used to address a forest. Okay. So simulation models, many different spatial patterns in different systems, they can be modeled using similar frameworks. Okay, and we are trying to create this so-called similar frameworks in this course, and they are called building block. A small number of building block models can generate many of the spatial patterns seen across a wide range of social and environmental systems. So when we know how to create these building blocks, they can be widely used in different scenarios, in social science, in ecological research, in environmental research, because these building blocks, they're just like small pieces of Lego toy, small Lego pieces, right? Before you're putting them together, they're nothing. They can be used anywhere, as long as there is pattern, as long as this piece is fit for a specific scenario, you can use it. So in this course, we're trying to discuss and learn how to build several commonly used building blocks. And from these building blocks, from these generally used simulation models, you can use them. You can use them for your specific research as long as the pattern matches. Okay, building block models to be covered this semester. Okay, aggregation and segregation processes, right? They can this type of processes, they can be used to address the expansion or the spatial distribution of, or you can say the structure of a city or a structure of a forest. Random walk processes, they can be used to address the foraging process of animals, or they can be used to guide a lot of things. We'll talk about that later. Okay, diffusion and growth processes. Growth processes, they are widely existing. They widely exist in our real life. For example, the growth of city. If you compare the map of Columbus area 20 years ago or even 30 years ago and today, you will see a very clear expansion of the city. But this model can only be used for city? No. For urban areas? No. If you observe the expansion of bacterial colony, you will say that the pattern is very similar to the growth of city. Okay, it means that models, they are tools. Simulation models, we create them as tools. As long as you add specific and proper context to them, you can use them widely in different disciplines and different scenarios. Okay, so generality versus realism. Detailed dynamic spatial models comes at some cost in generality and interpretability, but they provide realism and the ability to represent processes in specific geographic contexts. Okay, the model is a model. A model is neutral. As long as the pattern fits. As long as the model fits this pattern could be the expansion of a city, could be an expansion of a bacterial colony, could be the structure of a city, could be the structure of a forest. Okay, city, forest, or a bacterial colonies, they are all contexts. Okay, so the most important part is the building block, is the model itself, the neutral model. So next chapter, a more detailed discussion of the relationships between a pattern and a process. Okay, so this is the end of the first chapter of simulation and modeling in GIS. And thank you. See you in the next chapter.